This is Nwacc, Survey of the Universe, Lecture 22, Birth of the Universe. For Monday, April 20th, 2020. Please take notes on this lecture. There is a classwork posted to Canvas due tomorrow night. That is Tuesday, April 21st. It includes writing, and you must use your own words. So let us begin now, as we usually do with poetry. Say it with me. Sitting callously at the center of a galaxy, a black hole can swallow whole a star or become a quasar by heating the gas it's eating. When I say astronomy, you say rocks. Astronomy! Did you say it? Yeah, you did. How it all began. The Big Bang. So let's talk then about what the conditions were like in the very early universe. Telescope observation has told us for 100 years now that the universe is expanding, which suggests that at some time in the past it was much smaller, or at least everything we can see with our telescopes was much closer together. It was more dense in the past. And what happens when you condense a gas? Universe is mostly hydrogen gas. You heat it up. To compress a gas is to heat it up. So in the past, the universe was a lot more compressed, which means it was a lot hotter. What you're seeing here is a graph of temperature versus time. Let's look at these numbers. Temperature is in Kelvin. That's degrees Celsius, offset by 273. Here is 100 Kelvin. The temperature in the room right now is about 300 Kelvin, so that's right about there. And now we're going up 1,000,000 degrees, 1,000,000,000 degrees, 10 to the 9th, 1,000,000,000,000 degrees, 10 to the 12th, 1,000,000,000,000 degrees, 1,000,000,000,000 degrees, and I don't know any of the other words. It just keeps going up and up and up to 10 to the 32 degrees right after the Big Bang, one with 32 zeros after it. Now let's look at the x-axis. This too is what we call a logarithmic scale. That is, each bump on the scale is multiplied, not added. Same's true up here, right? Each bump is multiplied by 100. Here, each 2 bumps is multiplied by a factor of 10 to the 10th power, 10 billion. So 2 bumps multiplied by 10 billion. So here's the Big Bang, or right after the Big Bang. From here all the way up to here is just 1 second of time. This is 1 second after the Big Bang. So in 1 second, the universe cooled from 10 to the 32 degrees all the way down to 100 million degrees. And then bump over here at 10 to the 14 seconds. That's today. Or 10 to the 18 seconds. That's today. The universe is down to 3 Kelvin. Far away from the sun. So those are a bunch of big, weird numbers. What they really mean is that the early universe was extremely hot and dense. And as the universe has expanded, it has gotten cooler with time. And when matter is really hot and dense, it does some strange things. Remember, mass is a form of energy. You can convert mass into light. But the reverse is also true. You can convert light into mass. However, even a tiny, tiny particle like an electron contains a whole lot of energy in its mass, which means you need a really, really powerful photon to convert its energy into mass. In other words, you need a really hot photon. You need really hot conditions. So when matter is extremely hot, when the universe was extremely hot and it was mostly photons, some of those photons had enough energy to be converted to mass. And that's how particles formed. They formed from light. And they didn't form by themselves. They formed in pairs, and we know this. We can do this in laboratory. They formed in pairs. A matter particle, like an electron, and an antimatter particle, like an anti-electron, also known as a positron. Antimatter. It's not science fiction. It's real. We can make it in laboratory. Whenever you make an electron, you also make an anti-electron. Antimatter is just like normal matter, same mass, but it has opposite electric charge. So an electron is negatively charged, but an anti-electron or positron has positive charge. Well, an anti-electron and an electron have opposite charges. That means they attract each other. So as soon as they come into existence, as soon as their mass is created, not from nothing, but from the energy of light, as soon as their mass is created, they go away from each other, but very quickly come back because they're attracted electrically, and then they annihilate one another once again. When matter and antimatter meet, they annihilate one another. Their mass isn't destroyed, it is converted back into light. How much energy does it take to create mass? That's Einstein's famous equation, E equals mc squared. The amount of mass you're trying to create, the mass of an electron and positron combined, times the speed of light squared, is the amount of energy you need to bring those particles into existence. So that happened. The early eras of the universe are defined by what was going on in those eras. This is an often published diagram of the history of the universe. Right after the Big Bang, the universe very quickly got big, and then it slowed down in its expansion, but began expanding faster and faster with time. Early in the universe's history, the first 380,000 years, the whole universe was hot and dense enough to glow like a star. We now see that light coming to us as the cosmic microwave background. Well, that's today's lecture. Let's go in more detail. So the earliest eras are defined by the forces that were present. Different forces are stable at different temperatures. And then later eras are defined by what particles were present. Different particles are also stable at different temperatures. So, well, let's talk about all of physics. There are only 4 fundamental forces known to physics. All the other forces are subtypes of these 4. The weakest force is gravity, the curvature of space-time. Might seem strange, right? Is gravity the weakest force? Why is it then that gravity is what keeps you bound to the Earth and the Earth bound to the Sun? And the reason for that is that it takes something the size of the Earth to give you your weight. It takes something the size of the Sun to hold on to the Earth, the mass of the Sun, I should say. So gravity is weak because it takes a whole lot of mass to have any noticeable effect at all. The second force in physics that we don't care that much about in this class is called the weak force. It governs some forms of radioactive decay. When a uranium nucleus decays, it's because of the weak force, but that's not so important for this class. Electromagnetism, very important for your life. It is exactly what it sounds like, electricity and magnetism, but it also governs you. Electromagnetism is what prevents you from falling through the chair. There are electrons in your feet or in your butt, and there are also electrons in the floor or in the chair. The electrons in your feet are repelling the electrons in the floor, preventing you from falling through. That's the only thing preventing you from falling through. Electron repulsion, the electromagnetic force. It is the second strongest force known to physics. The strongest force known to physics is aptly named the strong force. That's what holds atomic nuclei together. There are 2 protons in a helium atom. Those 2 protons are repelling each other electrically because they're both positively charged. But there's another force inside the nucleus that holds them together, that overcomes electric repulsion and holds the nucleus together. That is the strong force. All right, here's a thought question. Which of the 4 forces prevents you from sinking to the center of the Earth? Is it gravity, electromagnetism, strong force, or weak force? Write down the answer, because I know you're taking notes. Yep, it's electromagnetism. Gravity is pulling you toward the center. What's preventing that? Electron repulsion. The electrons in your feet are repelling the electrons in the ground. So why is that important for the Big Bang? As you increase temperature, the 4 forces start to behave more and more identically. They become indistinguishable from one another. Some of this is known through experiment. Some of it is only theorized. Let's separate those. What we're seeing here are the relative strengths of the forces on the y-axis and temperature on the x-axis. Up here is 10 to the 15th degrees. So 10 to the 9th is a billion. 10 to the 12th is a trillion. So 10 to the 15th is 1,000 trillion, or a quadrillion degrees. We can do that in laboratory. Over here is 10 to the 29th degrees. Cannot do that in laboratory. Here is 10 to the 32nd degrees. Don't even try. The x-axis is also time after the Big Bang, because the universe cooled off with time. So this is 10 to the minus 10th seconds after the Big Bang, 1/10 billionth of a second. Here is 10 to the minus 38 seconds, 10 to the minus 43. At 10 to the 15th degrees, at a quadrillion degrees, the weak force combines with the electromagnetic force to become the electroweak force. This is proven in laboratory. It's remarkable that in particle accelerators today, we can reproduce the conditions in the universe 1/10 billionth of a second after the Big Bang. But there's a limit to how hot we can go in our laboratories. So beyond that, all we have are computer models. Beyond that, computer models tell us that at even higher temperatures, at 10 to the 29th degrees, 10 to the minus 38 seconds after the Big Bang, which we cannot do in laboratory, we can't get things that hot. But according to computer models, the electroweak force should further combine with the strong force to produce the grand unified theory force, the gut force. All right, cool. Well, we don't have data to back that up. All we have is computer models, so okay. Now, what happens at even higher temperatures, at say 10 to the 32nd degrees? Well, your guess is as good as mine. That's called the theory of everything. I should say theories of everything, really more like hypotheses of everything, because we don't even have a good unified theory about this. So, if you can figure that out, you get a Nobel Prize. So it might be that at extremely hot temperatures, 10 to the minus 32 degrees, the grand unified force will combine with gravity to produce the super force. All right. So let's relook at all of this in terms of time after the Big Bang. Was there a universe before the Big Bang? Was there even time before the Big Bang? Did time exist before the Big Bang? We don't know. Your guess is as good as mine. There might have been dragons there. There are some physicists, at least one, who suggests he has evidence of things that happened before the Big Bang. But other physicists dispute his interpretation of the data. His name is Roger Penrose, if you want to really take a mind trip and look that guy up. But we don't know if time even existed before the Big Bang. In fact, we don't even know what time was doing in the first era of the Big Bang, called the Planck Era, where the time is less than 10 to the minus 43 seconds. This is called a Planck time, 10 to the minus 43 seconds. And just for giggles, I'm going to type this time out in decimals. So this is a Planck time, we call it. That is how long the Planck era lasted. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 40. 1, 2, 3 seconds. That's how long the Planck era lasted. That is the smallest amount of time physics, as we know it, knows what to do with. We don't even know if time exists on smaller scales than that. Time might not exist at all. Time might be quantized, as we say. Time might come in individual chunks, individual pennies, and this is a penny. This is as small a time as might exist. It's the smallest time our theories of physics know what to do with. Maybe time exists on smaller scales. If it does, we have no idea. It could be dragons, could be devils, could be angels, could be anything. So when the universe was less than a Planck time old, if indeed it ever was, we don't know. Yeah. So it may have been that all the forces were unified into the theory of everything, the super force. But we don't really know. So your guess is as good as mine in the Planck era. We don't even have good theory as to what the universe was doing. Well, that's uncomfortable, but also exciting. Let's move on to an era where we at least have consistent theories and computer models to guide us. The Grand Unified Theory era, the GUT era. From 10 to the minus 43 seconds up to 10 to the minus 38 seconds. That's 0.37 zeros and a 1 seconds. At this time, the universe very rapidly cooled from 10 to the 32nd degrees down to 10 to the 29th degrees. Gravity is distinct from the other forces, but according to computer models, which is all we have for this era, the electroweak and strong forces were combined into the grand unified force. And for a brief moment, well, this whole era was a brief moment, but for a brief fraction of this moment, the whole universe, we think, was expanding much, much, much faster than light. We have good evidence for that, but not conclusive evidence. That's called cosmic inflation. We'll talk about that later. So the Planck era, we have no idea. Grand Unified Theory era, we have computer models but no data, so come back when you have some data. Let's move on to an era where we can actually reproduce the conditions in laboratory, the Electroweak era. From 10 to the minus 38 seconds up to 10 to the minus 10 seconds, 1/10 billionth of a second after the Big Bang. We can reproduce the conditions in the universe in laboratories 1/10 billionth of a second after the Big Bang, where the universe dropped down to 10 to the 15 Kelvin, 10 to the 15 degrees, 1 with 15 zeros after it. That is a quadrillion degrees. We can, briefly, reproduce these temperatures in laboratory. At higher temperatures than this, the electromagnetic force and the weak force are combined into the electroweak force. When temperatures drop below this, the electromagnetic force separates from the weak force. They become distinct forces. And during this era, as in our laboratories, particles and antiparticles are created from photons. For example, one way this happens, 2 gamma rays, the most powerful photons we know of, combine, and their energy gets converted to mass of an electron and a positron. And very quickly, that electron and positron recombine and become gamma rays again. So from the Electroweak era up to about 1/1000th of a second after the Big Bang, there were lots of particles in the universe. Lots of particles that had just been created from the energy of photons. Matter and antimatter in roughly equal amounts. But for some reason, and we still don't know why, and if you figure this out, Nobel Prize for you, for some reason, at the end of the particle era, there was a tiny excess of normal matter compared to antimatter. Because based on the argument I just gave you, if every electron is accompanied by an anti-electron, then all the matter and antimatter in the universe should have annihilated one another, and we wouldn't exist. Nothing would exist. And yet, telescope observations tell us that we exist. Your observations of the world, walking around, tell you that you exist. And the reason you exist is that for some reason we don't know, there was an asymmetry, the matter-antimatter asymmetry. For every billion protons and antiprotons, roughly one proton survived. So that's you. That's me. That's Earth. That's the sun. That's stars. That's all the gas in the universe are the leftovers. The leftover 1 in a billion protons and electrons that survived annihilation from antimatter. So at the end of the particle era, the antimatter was gone. It had all been annihilated. But it was still as hot and dense, not only as the inside of a star, but as the core of a star. It was as hot and dense as the core of the sun. Which means, what happens in the core of the sun? Nuclear fusion. Lots and lots and lots of nuclear fusion. In fact, about 25% of the protons, the hydrogen nuclei, remember hydrogen is just a proton, about 25% of all the protons fuse together to form helium and traces of other light elements like lithium and beryllium. So at 0.001 seconds, protons started coming together. One of the protons will flip into a neutron, and by about 3 minutes, helium will start forming. So the era of nucleosynthesis lasts for a few minutes. We can recreate it in laboratory, but exactly how long it lasted varies by model. Some models say as little as 3 minutes, some say as long as 20. So a few minutes. Well, after nucleosynthesis, there were nuclei. Mostly hydrogen still, but about 25% of that hydrogen had turned into helium with traces of other things. And the era of nuclei lasted for about 380,000 years. During this time, the universe was no longer hot enough and dense enough for nuclear fusion. That is, it was no longer hot and dense as the core of the sun. But it was still as hot and dense as the inside of the sun, which means during the era of nuclei, the whole universe glowed like a star. And this lasted for 380,000 years, until the temperature finally dropped from 1 billion degrees down to 3,000 Kelvin, the temperature of the coolest stars. At 3,000 Kelvin, 380,000 years, the universe suddenly was no longer hot and dense enough to glow. Electrons would float freely. And photons would float freely through space all the way to our telescopes. So that last moment when the universe finally became transparent, when it stopped glowing like a star, that light still hits us today. We call it the cosmic microwave background, the echo of the Big Bang. So once the universe became cool, electrons started combining to atoms. And then we had neutral atoms. The universe was transparent at this point, and we call this the era of atoms, as the universe cooled from 3000 Kelvin down to about 20. And this lasted for about 1 billion years, and after about 1 billion years, telescopes tell us galaxies started forming. So that began the era of galaxies that began 1 billion years after the Big Bang and remains to the present day. All right, so what happens in the universe is determined by the density and the temperature of the universe. As time went on from the Big Bang, the universe expanded and it cooled. Its behavior depended both on its temperature and its density. So how do we know? That is always a valid question in science. So the first clue that the Big Bang exists came in the 1920s when Edwin Hubble discovered Hubble's law, that the universe is expanding with time. But the Big Bang is not the only possible interpretation of that. There are 2 other pieces of evidence you have to add to that in order to say conclusively that the universe began with a Big Bang. First, we've detected the echo of the Big Bang, the leftover radiation, the cosmic microwave background. Second, we've detected the primordial elements that were manufactured during the era of nucleosynthesis. The primordial helium, the first helium ever made. Well, that's a little abstract. Let's look at it in more detail. It turns out that when Edwin Hubble discovered the universe is expanding, the Big Bang was not the only possible interpretation. That was one interpretation. The reason the universe is expanding, that is, the galaxies are getting far away from each other, is that if you turn back the clock, everything we see with our telescopes was really close together. That's all the Big Bang is. It says at some point in the past, everything we can see was condensed down into a tiny, tiny point. Not maybe or maybe not infinite density. Maybe, maybe not. Big Bang Theory doesn't require infinite density, but it allows for it. But there's another suggestion, or there's another possible interpretation called the steady state hypothesis. The steady state hypothesis says that the reason the universe is expanding is that it is infinitely old and infinitely large, and all the time new space is being created. And in that new space, new matter is being created. So how do we tell the difference? How can we test between the Big Bang hypothesis, which we now call the Big Bang Theory, and the steady state hypothesis? And the way we do that is by looking for predictions that can be tested. The Big Bang hypothesis made 2 predictions. First, the cosmic microwave background. According to the Big Bang hypothesis, if you turn back the clock far enough, the universe, the whole universe, was hot enough and dense enough to glow like a star. And remember, when you look far away in your telescope, you're looking back in time, which means we should be able to see with our telescopes all the way back to the point when the universe was hot enough to glow like a star. The light that was released when the universe finally cooled down to where it was no longer glowing should still be reaching us. We should see it with our telescopes. However, it wouldn't look like visible light. When the universe was hot enough to glow like a star, it would have glowed a lot in the visible light and in the infrared. However, the universe has expanded since then, and the light waves have expanded to longer wavelengths en route to us. So what we should see is not infrared and visible light. What we should see is microwaves surrounding us, shining on us from every direction. And indeed we do. The cosmic microwave background, the echo of the Big Bang, was discovered in 1964. It was the nail in the coffin for the steady state hypothesis. The steady state hypothesis had nothing to say about the cosmic microwave background, but the Big Bang hypothesis predicted it, and it came to be observed. So when the universe was hot and dense, those electrons could not bind to the atoms. So the electrons were absorbing light and emitting it and absorbing it and emitting it and absorbing it and emitting it. In other words, just like inside the sun, the universe was not transparent. It's like the sun is not transparent. But when the universe expanded enough and got cool enough that the electrons could bind to the protons, then all that light was released. And we can still see it today. Although it was released at 3,000 Kelvin, visible light, infrared light mostly, but a lot of visible light too. Since then, as that light has traveled the long distance to our telescopes, it has expanded to longer wavelengths, 1,100 times longer. Microwaves. Remember, you can tell how hot something is by its brightest color, its brightest wavelength. The cosmic microwave background has a thermal spectrum, so it has a temperature. And that temperature today is about 3 Kelvin, 3 degrees above absolute zero, or like 2.73. What does it mean for radiation to have a temperature? It means that if you take an asteroid and you fling it far out into deep space, far away from our sun, far away from the galaxy even, far away from any source of light, any source of heat, where there's nothing shining on it except the cosmic microwave background. That asteroid will get colder and colder and colder until it reaches 2.73 Kelvin. Light from the cosmic microwave background shining on the asteroid will keep it at this temperature. This is an all-sky map of the cosmic microwave background. We have 2 satellites in orbit that have given us lots of data on the CMB, the Planck satellite and the Wilkinson Microwave Anisotropy Probe, WMAP. So, that is one prediction of the Big Bang hypothesis that was later observed. If you turn back the clock, the universe was hot and dense enough to glow like a star, and we should still see that radiation. And we do. The cosmic microwave background. The second prediction that was made by the Big Bang hypothesis was that if you turn back the clock even farther, the universe was not only hot and dense enough as the inside of a star, it was hot and dense enough as the core of a star. Not only was it hot and dense enough to glow like a star, it was hot and dense enough for nuclear fusion, turning element number 1 into element number 2, hydrogen into helium. Which means, according to the Big Bang hypothesis, the very first galaxies, the first stars that turned on, even though the stars have not yet had enough time to produce any helium, there should already be some. The very first galaxies should be about 25% helium by mass. We should see the spectral lines of helium in the very first galaxies. And indeed, we do. Big Bang nucleosynthesis. Nucleosynthesis means the building up of heavier nuclei from lighter ones. This happened shortly after the Big Bang. Protons and neutrons combined to form deuterium, heavy hydrogen, and those deuterium, through a long process, built up to form helium. So the Big Bang predicted 25% of the hydrogen in the universe should have fused together to form helium. And observations confirm this. So let's do a thought question. If it's really true that the Big Bang fused 25% of hydrogen, protons, into helium, which of these abundance patterns would be unrealistic for a main sequence star? 28% helium, 5% helium, 25% helium, or 27% helium? Write the answer down. Oh, you said 5%. You were right. The early universe, right after the Big Bang, turned 25% of hydrogen into helium. So all the main sequence stars today will have at least 25% helium. Maybe more than that, because remember, stars make even more helium. So you could have 25 or 27 or 28, but you're not going to have 5% helium in a main sequence star. Oh, you can have one in an exotic star, like a white dwarf, right, where all the hydrogen and helium have been blown out into space. They've gotten rid of their helium. It's not that they never had any. So this is the second piece of evidence that confirms the Big Bang hypothesis. The second prediction that the Big Bang hypothesis made that was later confirmed. The primordial abundance of helium and other light elements. So, evidence for the Big Bang theory. The first clue was that the universe is expanding, which suggests that it must have been smaller in the past. And when I say smaller, I mean everything we see with our telescopes was smushed together. The Big Bang hypothesis made the two predictions. Number one, that if you turn the clock back far enough, the whole universe glowed like a star, and we should still see that light, and we do. Cosmic microwave background. Second piece of evidence, or the second prediction, if you turn the clock back even farther, the universe was hot and dense as the core of a star. Nuclear fusion turned hydrogen into helium, and we should see that helium in the earliest galaxies, and we do. So as successful as the Big Bang hypothesis was at predicting things that would later be confirmed, it wasn't perfect. Scientific theories never are. Or if they seem like they are, well, turns out often later they're found that they're not. Not that they're complete BS, you just got to modify them. And the Big Bang hypothesis, which was later elevated to the Big Bang theory, had to be modified. It was modified by a feature we call inflation. Shortly after the Big Bang, the whole universe expanded much, 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 much faster than light. Why do we think this? Well, to understand how the concept of cosmic inflation came to be, we have to look at some cracks in the original Big Bang theory. Even though it was great at predicting things that were later observed that no other theory that we had could predict or even explain, it wasn't perfect. There were cracks in it. There were problems with the original Big Bang theory. When you look at the largest structures in the universe is laid out like a foam. Galaxies are in clusters. Those clusters of galaxies are in superclusters, clusters of clusters, and those superclusters are laid out like a foam. Why is that? The original Big Bang theory had nothing to say about that. There's another problem with the Big Bang theory, the uniformity problem. The cosmic microwave background at that end of the sky has the same temperature as the cosmic microwave background at the other end. And yet, light from that end of the universe is just now reaching us. light from that end of the universe is also just now reaching us, which means light from that end has not yet had time to tell that end what temperature it is. Things come to thermal equilibrium, that is, the universe communicates its temperature through photons, through light. So if this end of the universe hasn't yet had time to send light to that end, how does this end know what temperature that end is? How can they be the same temperature? Yes, the Big Bang hypothesis predicted the cosmic microwave background should exist. It did not say it should all be the same temperature. But it is very close to the same temperature. There's another problem with the original Big Bang hypothesis. As far as we can tell, as far as we can measure, the universe is flat. What does that mean? A curved universe is one in which light travels in a curve. A flat universe is one that, on the largest scales, light travels in a straight line. The original Big Bang hypothesis said the universe could be any geometry at all, flat or curved. In fact, there are a lot more ways for the universe to be curved than to be flat. Flat is very specific. Why should it then be flat? All of these mysteries are serious mysteries if you don't take inflation into account. But if you modify the Big Bang theory to include cosmic inflation, boom, all three of these mysteries are solved. So let's start by looking at what inflation is. Shortly after the Big Bang, fraction of a second after the Big Bang, the universe expanded much faster than light. Then it slowed down to sublight speed. It slowed down, continued expanding, and then started accelerating again, but not to light speed. So during inflation, according to the data, the universe grew 10 to the 30 times larger, 1 with 30 zero times larger than before, almost instantaneously, fraction of a second. Now, how big the universe was when this happened depends on the model. There are computer models which are all consistent with data, yet contradict each other or conflict in answering the question, how big was the universe when this happened? They all say it was very small when it happened. One model says the universe grew from the size of an atomic nucleus to the size of the solar system, like that. When I say the universe, I mean the observed universe, everything we can see with our telescopes. And this happened when the universe was about 10 to the minus 36 seconds old, and it lasted for 10 to the minus 33 seconds. So let's talk about how inflation solves the problems. This is a computer model of the largest structures in the universe, superclusters of galaxies. It matches what we see with our telescopes very well. That's why it's a famous model. The Milky Way, in fact, is part of a supercluster of about 100,000 galaxies, and superclusters fill the universe like a foam. But why? Well, inflation solves that problem. Before inflation, the whole universe was so hot and so dense that particles overlapped each other. That happens in the small world, in the quantum world. Particles overlap each other, and when they do that, they are laid out like a foam. Some spots are a little denser than others. Some spots have more overlap between particles than others. Before inflation, the universe was a quantum foam. Once expansion happened, once inflation happened, those tiny overdense spots became galaxy superclusters. Those tiny overdense spots were seared into the fabric of the universe. The structure of the universe was determined before inflation. That foam-like structure was already there before inflation, and it was seared in as the universe expanded faster than light. Those overdense places became places where there was a lot of matter, which then condensed to form superclusters of galaxies, which then further condense to form clusters, further condense to form galaxies, further condense to form stars. Inflation also solves the uniformity problem. That is, why is it the cosmic microwave background is almost the same temperature every direction you look? That's strange, because the part of the cosmic microwave background on this end of the universe is not in what we say thermal contact or causal contact with the other side. Light from this end of the universe is just now reaching us. Light from this end has not yet had time to reach the other end. So they shouldn't know each other's temperature. They should not be the same temperature. But inflation solves that problem. Inflation says before inflation, the whole universe was in thermal contact with each other. Before inflation, the whole universe was in thermal equilibrium. In other words, the whole universe was the same temperature. After inflation, then, quite suddenly, distant parts of the universe are no longer in contact with each other, but they're already the same temperature, too late. And then all parts of the universe, even though they're not in contact with each other, cool down at the same rate. So before inflation, the whole universe is the same temperature. After inflation, because they were before, they still are, and they're cooling down together, even though they're not in contact with each other. Well, that's two mysteries solved by inflation. The third mystery is the geometry of the universe. Remember, gravity is the curvature of space-time. We know that space-time can bend and twist. But what's the shape of the universe overall? Let's first look at the three possible geometries of the universe. A flat universe is one in which, on the largest scales, light travels in a straight line, assuming it doesn't get too close to a star or a black hole or a cluster of galaxies or some gravity source. That's a flat universe. Light travels in a straight line. A closed universe is one in which light travels in loops. And an open universe is one in which light deflects over the longest scales but doesn't close back in on itself. And again, we can't diagram four-dimensional space-time curving into a fifth dimension, so we tend to diagram space-time as a two-dimensional surface that might be curved with respect to a third dimension. So a flat universe is a plane, a closed universe is a sphere or some closed shape, an open universe is a saddle. Well, why should the universe be flat? The Big Bang hypothesis said it could be any geometry at all. In fact, the conditions in the early universe would have to be really fine-tuned to make the universe flat, according to the original Big Bang hypothesis. But with inflation, the universe could be any geometry at all, and when you inflate it, it flattens out. It's like a balloon, like blowing up a balloon. Say you're an ant on a balloon. Well, maybe this ant can see the curvature of the balloon, but if you blow the balloon up large enough, then to the ant, the balloon looks flat. Just like to you, looking around, the world looks flat. Not because it is YouTube, but because the Earth is so large that the part that you can see is almost flat and looks flat to your eyes. Likewise, inflation solves the flatness problem of the universe. What it says is the universe, the global universe, everything that exists might be open or closed, but it inflated so much that the part we can see with our telescopes is very close to flat. So this brings us to an ambiguity in a word that we've been taking for granted this whole semester. Universe. The word universe is ambiguous. So let's divide the word universe into three subcategories. The observed universe, the observable universe, and the global universe. Some sources will combine observed and observable, but I'm going to separate the two concepts out. In this class, when we say universe, so far we've been talking about the observed universe. That is what we can see with our telescopes. Everything between here and the cosmic microwave background. The cosmic microwave background is the limit of what we can see with telescopes. We can't see beyond it, because beyond the cosmic microwave background, before the cosmic microwave background, the universe wasn't transparent to light. Light couldn't penetrate. So no matter how good our telescopes get, we're never going to see beyond the cosmic microwave background. That's the observed universe. However, there is another way to probe space-time that theoretically could see beyond the cosmic microwave background, not using light, but using gravitational waves. Gravitational wave detectors are brand new. They just came online in 2015. And right now, they can't see anyways near as far as the cosmic microwave background, but theoretically they might. And so the observed universe might expand beyond the cosmic microwave background. In fact, it might, theoretically, given enough technology, expand out to almost the cosmic event horizon. Remember that the universe is expanding. The farther away we look, the faster space is expanding from us. The faster galaxies are receding from us, or appear to be, because space is expanding. There is a distance at which the universe is expanding at light speed, and more matter is crossing that boundary, which means we'll never be able to see it. We call that distance the distance at which space is expanding at light speed, and therefore we can never see beyond it, no matter what kind of detectors we have. Not with telescopes, not with gravitational wave detectors, nothing can see beyond the cosmic event horizon. That marks the boundary of the observable universe. And again, some sources will conflate observable and observed. They'll use one definition or the other. The cosmic microwave background or the cosmic event horizon. But I'm separating the two. So the cosmic microwave background is the boundary of the observed universe, what we've actually seen with our telescope. The cosmic event horizon is the boundary of the observable universe, what we might hypothetically see with our gravitational wave detectors. But if inflation is true, and the evidence seems to suggest, though not conclusively, that it is, that tells us that the global universe, the true universe, everything that exists, is much bigger than the observable universe. And that's why the observable universe looks flat. I should say why the observed universe looks flat. It's much bigger than the observed universe. Just like your observed world, what you see with your eyes, looks like a flat Earth, even though it's not. It's just that the Earth is much bigger. But on the global Earth scale, we know the Earth is closed. It's round, right? It's a sphere-ish. So the global universe may be as well. It may be closed, or it may be open, or it may be flat. It might be finite. It might be infinite. We don't know, because we can't see beyond the cosmic microwave background. And the farthest we can ever hope to see with gravitational wave detectors is the cosmic event horizon. So remember, energy is conserved, at least after the Big Bang. Inflation did not change the total energy of the universe. The total energy remains constant. Inflation only changes the energy density. And the energy density determines the shape of the universe. Was conservation of energy broken at the Big Bang? We don't know. All right, so inflation has solved three giant mysteries. It's solved three giant problems with the original Big Bang Theory. So, is it real? Well, in physics, how much prestige your awesome new view of the universe has depends on the level of confirmation it has had. The Big Bang hypothesis, for example, explained things that had already been known the expansion of the universe. That is step one. You've got to explain everything that's already been seen. You can't be contradicted by any data that's already been there. Explanation. Great. But the Big Bang went to step two. It predicted things that had not yet been observed and could not be explained with the competing hypothesis, the steady state. It predicted the cosmic microwave background and the primordial abundance of helium, which the steady state hypothesis could not. So because it made successful prediction, we have maximum confidence that it is in fact correct. In some form. Details are still being worked out. Let's compare that to inflation. It's got step one down. It explains things that have already been seen. In fact, it explains three great mysteries. The structure of the universe, why the universe is laid out like a foam. The uniformity of the cosmic microwave background, why it's the same temperature at that end of the universe as it is at that end. And the apparent flatness of space-time. It explains all three of those. But it has not yet made any major successful predictions. It has not yet predicted anything that has later been observed. So it has not yet taken the next step in its glorification. So inflation, we have medium confidence, maybe medium high, probably, but really come back when you predict something. So inflation explains structure of the universe, uniform temperature of the universe, cosmic microwave background anyway, and the flatness of the observed universe, though we don't know if the global universe is flat. So observations are consistent with inflation, but it hasn't yet predicted anything major that's been shown, that's been confirmed. So Big Bang, yes. Inflation, probably. Oh man, we made it through the birth of the universe. So let's end now, as we usually do, with poetry. Say it with me. Long before man laughed and sang, the universe began with a big bang. As space expanded, things cooled down. Now space is cold as the cosmic microwave background. When I say astronomy, you say rocks. Astronomy! Did you say it? Yeah, you did. Here are some summary slides to help you when you study. Here's another one. Here's another one. There is classwork posted. Go do it now while the material is fresh. I'll see you next time.